Let's look at the potential intensity of cyclones. Essentially, since the 1940s, it's been known that the temperature threshold for tropical cyclogenesis has to be above 26 degrees centigrade. Subtropical storms and extratropical storms, of course, can get their energy from the baroclinic instabilities, what we call baroclinic cyclogenesis, but they are elevated vortex structures which have to eventually reach the surface and then have to intensify if they are to be tropical cyclones, which in the case of subtropical storm example we saw, for example, as one of the cyclogenesis mechanisms. And here, when you think of making predictions, for example, we talked about whether cyclogenesis itself can be predicted ahead of time, and there are some evidences that maybe it is possible. But once the tropical storm has formed with stronger than 17 meter per second winds, and you know something about the environments, the models are able to predict now the tracks, the intensities, and so on. But theoretically, you still need to know what is the potential intensity a tropical cyclone can attain given all the conditions: sea surface temperature, vertical shear, moisture loading, and lapse rates, and so on and so forth. So the early theories of potential intensity included what is called CISC, convective instability of the second kind. There is a convective instability of the first kind, which just looks at temperature profiles. So you can either warm the surface and force the air to rise, or you can cool the top of the profile and then create instabilities that way as well. In the second convective instability of the second kind, basically temperature profile is also combined with the moisture profile, so that moisture and latent heat release, condensation, heating intensifies the cyclones. The context in the case of cyclones for CISC is that given an incipient low-level cyclone with a moist boundary layer, it's the frictional convergence. Remember, we still need cyclonic flow coming in, and it's near the surface, so the friction is important. So it's slowing down as it enters the incipient vortex to feed moisture to the convection that's trying to support it. Then latent heating due to convection reduces surface pressure, strengthens the low-level cyclone, and enhances moisture convergence and convection in a positive feedback loop. Okay, so here is the incipient disturbance. There is the cyclonic convergence happening into the low pressure system. Frictional convergence of moisture supplies the rising air, and latent heat release causes air to expand and the surface low to strengthen. So the low pressure at the surface gets strengthened. So here convection grows stronger as more moisture flows into the surface. But every time you have such convergence, you have to remember a few things, that angular momentum conservation, especially away from the friction, has to be considered. Plus the air that is flowing in is getting into a lower pressure region, so it is likely to expand and condense, and if you have to maintain the moisture supply, you have to add additional air and moisture along the way, which can happen by evaporation, right? We'll see more of this when we talk about the Carnot Cycle theory for potential intensity. So at the top, air flows outward, and Coriolis turning forms the upper anticyclone, and typically here, as surface low strengthens, moist frictional convergence, convection, and surface low have positive feedback to each other, as we said here. Winds strengthen as the low develops, and frictional convergence is able to maintain the moisture supply. So stronger convection gives more latent heat flux. There are details because the circulation is faster here. Near the surface is where you get maximum winds in tropical cyclones, unlike the extratropical cyclones, as you remember. So the angular momentum that is brought in has to be explained as it goes up because the winds slow down at the top. So in the actual cyclone, and not just convection or incipient vortex, the angular momentum has to be conserved. So that means the distance from the eye has to increase. So the eye wall has to tilt, as we saw before. And that kind of leads us to the second theory, Vichy. It's the Carnot Cycle theory of potential verticity, that is wind-induced surface heat exchange. These theories are also used in MJOs, for example. Okay, so here we are. Carnot cycle basically assumes a closed loop where thermodynamic energy is converted into mechanical energy of producing the winds, which then dissipate away by various mechanisms, right? The schematic of energy flux in a tropical cyclone, idealized as a Carnot engine. Air in the atmospheric boundary layer, bottom right to left here, flows in isothermally. So there is an assumption right off the bat that the boundary layer is isothermal, which it is not in reality. Rises up adiabatically in the eye wall of the convection, which is a fairly reasonable assumption, because if the air parcel is moving fast enough, it doesn't have time to mix with the environment, so it can rise almost adiabatically. Flows out to great distance isothermally near the tropopause, then sinks far from the storm and then comes back. So this is the loops that's assumed. The temperature near the surface is assumed to be, let's say, in equilibrium with SST, so essentially the same, or maybe just a fixed difference. So you have warm temperatures coming in, rising, and getting a very cold temperature here because of the rising, expanding condensation, rainfall, and then drying and radiative loss and all those good things, giving you very cold temperatures. So you have these loops, A to B, B to C, C to D, and back to A. That's our Carnot cycle, and the temperature difference is pretty massive. So if this is determining the thermodynamic energy available, then obviously that can help the mechanical energy production in terms of the intensity or potential intensity, right? And you can see the tilting of the eye here that can explain the angular momentum conservation of fast air coming in closer to the eye wall, VR kind of term, and then as the V slows down, to maintain VR you have to go away from the eye, so obviously there is a tilting, and that is observed in reality as well. So the four branches of the Carnot cycle here are then isothermal inflow of surface air, moist adiabatic ascent in the eye wall, convection and outflow just below the tropopause, sinking of cooled air in the environment far from the tropical cyclone center to close the system. The cooled air is assumed to return to the tropical cyclone environment adiabatically in the loop D to A. We know that there is compression and heating as the air sinks, and we know that this is not an isothermal situation, and as we said, air is moving from out here, let's say with environmental pressure and winds, and it's looping in cyclonically to converge into the eye wall. So there is friction, there is moving towards low pressure, so expansion. So along the way, air has to be added and moisture has to be added. There are frictional effects, air bubbles jumping out of the ocean into the lower atmosphere. So all those processes are actually going to make it not only an open system, but also break your assumption of an isothermal convergence into the eye wall. But nonetheless, it's a question of whether these mechanisms can explain observed potential intensities that are achieved by the storms based on the estimates of these thermodynamic energies by measuring temperatures near the surface and top of the atmosphere and so on. And it turns out that they can do a fairly decent job. Okay, Here is a photo of the sloping eye wall of Hurricane Ivan. It's not a very clear picture, but nonetheless you can get a sense of the sloping of the eye wall. So that is a real process. We can calculate the efficiency epsilon of the tropical cyclone Carnot engine to determine the friction of the heat energy that can be converted into mechanical energy. Using typical values for SST and tropopause temperatures in the figure that we just looked at for the Carnot loop, Carnot cycle, we can solve for epsilon. So T in minus T out, T in at the surface, T out at the tropopause in the cirrus cloud, divided by T in. So you can assume this is approximately equal to the sea surface temperature, minus T out is the tropopause temperature divided by SST. So let's say 300 minus 200 divided by 300 as typical numbers. That's about 1/3. That's the efficiency with which the Carnot cycle is converting the thermodynamic energy to mechanical energy, which can explain the potential intensity of the cyclone. Okay, so you get the idea that the actual cyclone is growing in the real environment. It's not isolated, and there are many details involved. For example, angular momentum and the moist potential temperature. You have potential temperature and equivalent potential temperature. So as the air converges in on angular momentum surfaces and rises, and angular momentum has to be conserved, and the equivalent potential temperature has to be explained. All those relations between angular momentum surfaces and theta E, equivalent potential temperatures, have to work together for assumptions of adiabatic ascent and the outflow and then sinking and convergence. Not everything works perfectly, but the Carnot cycle mechanism does explain the potential intensity. Of course, when we do the model, we are not when we do forecasting with models, we are not explicitly putting in CISC or Carnot cycle. Convective parameterizations do involve some of the elements of CISC and Vichy. How the convection is triggered in the models is not from first principles, so they do have assumptions that are related. Nonetheless, to the extent that the models are successfully forecasting cyclone tracks and potential intensities, then you can go back and diagnose what processes work. Oftentimes, obviously, it's not one or the other. CISC can be working in the convections of the eye walls and the outer bands, for example. Here we are only focusing on the eye wall as potential intensity, but obviously this cyclone has larger structure. And Vichy is also working because as the winds are converging frictionally into the eye wall, there is surface heat exchange that is wind induced, and there is a positive feedback between frictional convergence, moisture feedback, convection, latent heat release, pressure drop, and so on. So it's a matter of almost like looking for consistency checks, but for idealized studies, people do look for which mechanism may better explain potential intensities. Okay.